Okay, let's continue with this theorem. Remember, at the end of last lecture, we stated this theorem: if R is a commutative ring with 1, then the following are equivalent, namely R is a R is a field, as a the polynomial ring is Euclidean domain, or polynomial ring is PID, and 1 implies 2. Oops, these should be 1, 2, 3. This should be 1, 2, 2, 3, 3, 1. 1, 2, 3. So we should do this way. So we already 1 implies 2 is proved about theorem, and 2 implies 3 is that every Euclidean domain is PID. Again, as we proved above, and now we will prove that 3 implies 1. Namely, if R of X is a principal ideal domain, then R must be a field. So let's assume that. So assume that R of X is a PID. So remember, R is commutative ring with 1. So we only need to show that every non-zero element of R is a unit. We only need to show that every non-zero element of R is a unit. So for this purpose, let A be what A be a non-zero element from R, and consider the ideal divided by A and X, polynomial X. Consider this ideal, the ideal generated by A and X. So remember, this is the ideal A times f of X plus X times G of X, where f of X and G of X are in R of X. Okay, that is I of X, I. So this is the ideal generated by A and X, the polynomial X. Since Rx is a principal ideal domain, then there is a polynomial f of X in R of X. There is a polynomial such that this I is generated by this f of X. So this implies that A is in f of X and X is in f of X. So that we may write A is equal to f of X times some other polynomial G of X. And X as f of X times some other polynomial H of X, for some polynomials f of G of X and H of X in R of X. So now this f of x times this A is equal to f of x times g of x. This is not 0. So that if you look at the degrees, degree of A is 0, so that it is degree of f of x times g of x is degree of f of x plus the degree of g of x, so that both of them are 0. So that degree of f of x is 0, degree of g of x is also 0. So that means f of x is some constant in R, but not 0, of course. Now we may write x is equal to, so from this identity, we have x equal to b times h of x. So this implies that the degree of x is 1, degree of b is 0, so the degree of h must be 1. So that h of x is c plus some dx. So that x is equal to b times c plus dx, which is b times c plus b times dx. So this implies that, in fact, c is equal to 0. And this implies that there is no constant term on the left-hand side, so that b times c is equal to 0. B is not 0, so that c is equal to 0. So let me write like this: b of bc is equal to 0 implies that c is equal to 0, and b times d is equal to 1. Also, this coefficient of x is 1, so b times d is equal to 1 implies that b is unit. So I is equal to b. B is unit, so that it is everything. So since it is unit, the ideal generated by that unit element is the whole ring. But now 1 is in R of x. R of x is I in I is equal to I, and this is generated by a times x by assumption, so that we may write 1 as a times f of x plus x times, so f1 of x, f2 of x. And if we write it like this, suppose that f1 of x is c0 plus c1x plus c2x squared, blah, blah. Well, this is x times d0 plus d1x, blah, blah. So that this is a times c0 plus a times c1 plus d0 times x, etc. So that a times c0 is equal to 1. So that means a is unit. We don't need that. There's 0. A is unit, so that A is unit. So we showed that every non-zero element of, so what did we have above? Let's go back. So here we had a non-zero element of R, and we need to show that this element A is unit. So we concluded that this element A is unit. So therefore, R is a field. If you have a commutative ring with 1, which is in which every non-zero element is unit, so that it's automatically, in this case, R has automatically has no zero divisors, so that R is a field. R is a field, so that this finishes the proof of the theorem. So that 3 implies, we proved 3 implies 1. Okay, and corollary is z of x is not PID, which we proved before. Before we remember, we showed that the ideal generated by 2n x is not principal. We proved this before, but it also follows from the above theorem. Since z is not a field, z of x is not a PID or UFD, either one. Okay, the proof, z is an integral term. Z is not a field. And apply above theorem. Okay, here's another corollary. If f is a field, then if you look at the polynomial with two variables, which we did not talk about this, but if you take a ring to be f of x and look at the polynomial over this f of x, then that is f of xy. This is not a principal ideal domain. Proof. This f of xy, f of x in R is not a field. So this implies that R of y, which is f of xy, is not a PID. Because if R of y was a PID, then R would be field. Okay. So as a result, we have, this is when you have a field, then f of x is not field, but PID. Let me write like this. Then if you look at f of x, y, this is not PID. Okay, f of xy is not PID anymore. Now, what is that? What are this? Let's see, what is this? Let's see. So let me give one definition. Noetherian ring. So that is the definition. Let R be a ring. R be a commutative ring. Usually commutative. R is called Noetherian. Noetherian if for every ascending chain of ideals, ascending chain, that's an increasing chain of ideals like this, of infinite many ideals, Not necessarily distinct, of course. So this, whenever you take such a sequence, it should stabilize at some point. So that means there is a k. There is a k. There is an index k such that for all ij is equal to ik for all j is greater or equal to k. Namely, here so that the sequence should be something like this: I1, I2, and then you have ik, and after that it is ik plus 1. Next one is ik, ik. It goes. Next one is ik plus ik. Next one is ik, etc. So all the rest is equal to ik. So you cannot find properly increasing sequence of ideals. Here's a proposition. Proposition: if R is a PID, it's a principal ideal domain, then it is Noetherian. This is an important notion, again, Noetherian. So here's a proof. So let I1, I2, I3, etc. be an infinite chain of ideals. Chain means it is increasing like that. Then if these ideals are inside one another, then if you take their union, in general, the union of two ideals is not an ideal. But if one of them is inside the other one, then it is union is an ideal. Then the union I is from 1 to infinity this ai. This is an ideal. You should check it. This is an ideal in R. Since R is principal ideal domain, R is a principal ideal domain. There is an A in R such that I is equal to A. I is equal to A. So that A is in I. This implies that A is in the union of AIs. So that A is in one of those AIs. So that there is a K such that A is in IK. But this implies that this A is inside IK, the ideal generated by IK. Now, for any J is greater than or equal to K, sorry, J is greater than or equal to K, namely like this. So A is inside IK, IK plus 1, etc. IJ. But they are all inside I, but I is equal to I is generated by A, so that all these containers must be equality. So that IK is equal to IK plus 1, IK plus 2, etc. So namely for any, so let me write here. Namely, if J is greater than or equal to K, then IJ is equal to IK. So therefore, the increasing sequence of ideals stabilizes. So therefore, R is Noetherian. So, okay. So That is Noetherian. Now let's give another notion. Let me write or use different colors. Color this unique factorization domain. Oops. Or for shortly, we will write UFD. So that is a definition. Okay, let me continue with this colors. This is nice. So an integral domain in integral domain R is called the unique factorization domain if two things are satisfied. If every non-zero, non-unit, non-zero, non-unit element is a product of irreducible elements. And every irreducible element is prime. Okay. So example, if you take R to be Z, let N to be an integer, not zero, and not unit. So units are plus or minus 1. Then let N be irreducible. Suppose N is irreducible, so that N is equal to A times B implies that one of them is or B is equal to plus or minus 1. So that means N is that means that N is P or N is equal to minus P for some prime P. So prime numbers are positive prime numbers in the number theory that we know. 3, 5, 2, 3, 5, 7, etc. In this sense. So that irreducible elements are irreducible elements in Z are plus or minus P's where P is prime. So these are irreducible and non-unit element, of course. So that every irreducible element, every positive number, so every positive and greater than 0 is a product of a greater than or equal to 1, let's say, is greater than or equal to 2, is a product of primes, as we know, prime numbers, so that if the absolute value of N is greater than or equal to 2, then N is, we can write N as plus or minus 1 times P1, P2, PR, where PI's are prime, as we know. Now we will do this and this is PIs are prime and unique. PIs are unique up to order. So here is what we mean. For example, if we take 30, for instance, minus 30, you can write you can write it is minus 1 times 2 times 3 times 5, right? Or it is, if you like, this is I wrote unit here, or you can write minus 2 times 3 times 5, etc. Or it is, we can forget about this one, 2 minus 2, for instance, or minus 3 times minus 5, for instance. So that these are unique up to this, up to sign, up to multiplication by a unit by minus 1. Okay, so here is a proposition for this. If R is a PID, then it is UFD. It's a unique factorization domain. So there is a reason for unique factorization domain, which we will see in a moment. Remember our previous picture that we drew a couple of lectures ago, in the last lecture perhaps. So if we have Euclidean domain, let me do it here, Euclidean domain, they are inside, every Euclidean domain is inside our principal ideal domain, PID, and this is also now we have UFD also inside integral domain. So all of them are integral domain, and we have a picture of something like this. Euclidean domains are PID, PIDs are UFD, UFDs are okay. Here's a proof of this proposition. So since R is RPID, this implies that every irreducible element is prime. In a PID, every irreducible element is prime, so that if R is PID, then so in order to show that this is a UFT, we need to show that it satisfies these two properties, so that it satisfies the second property, so that since it is PID, principal ideal domain, every irreducible element is prime. So we need to show this first property now. So let's define. Now show that we will show that every non-zero, non-unit element of R is a product of irreducible elements, right? We need to show that. Oops, what happened? So we need to show that every non-zero non-unit element is a product of irreducible elements. Product. Okay. Product of irreducible elements. So we show that every non-zero non-unit element of R is a product of irreducible elements. So for this, let's define a set X, which is R and R minus 0, such that R is not unit, and R is not a product of irreducible elements. So we will show that, claim that this X is empty. So that if X is empty, that means every non-zero, non-unit element of R, capital R, is a product of irreducible elements, so that it will be a UFD. So suppose that, claim this. So assume that this is not true, that X is not empty. Suppose X is not empty, so that, note that if A and B are not in X, then A times B is not in X either. The reason is that because if A is not in X, that means you can write A as a product of irreducible elements. And you can also write B as a product of irreducible elements, so that you can write A times B as a product of irreducible elements, so that A times B is not in X. So A is product of irreducibles. Since A is not in X, B is not in X, so that it is a product of irreducibles, finite dimensional irreducible elements. Of course, A times B is a product of irreducibles. Oops. So that means A times B is not in X. So this the contrapositive of the statement is that if A times B is in X, this implies that A is in X or B is in X. One of them is in X. Just like prime ideal. Okay. Of course, X is not an ideal. Now, since X is not empty, choose an element. A1 in X. So that A1 is not 0, and it is not unit, and it cannot be written as a product of irreducible elements. So that A1 is itself is not irreducible. So A1 is not irreducible. So that means we can write A as A1 as A2 times B, where A2 is non-unit, non-zero non-unit, and B is non-unit. So we can decompose like that. Now, so that A2 times B is in X, because it is A1. But so by the about this property, A2 is in X or B is in X. So without loss of generality, we can assume A2 is in X. But A1 is equal to A2 times B implies that A1 is inside A2, and since B is not unit, they are not equal. Now do the same thing for A2. So inductively, so we can find A3, A4 in X such that A1 is inside A2. This is inside A3, etc. By the above argument. So that means we have an increasing sequence of ideals which does not stabilize. So we have an ascending chain of ideals. Chain of ideals which does not become constant after a certain place. Increasing, this is increasing, so that means R is not Noetherian. But this is a contradiction because every principal ideal is Noetherian. Since R is a PID, it is Noetherian. This is contradiction. Contradiction to R. So PID, R is PID. And PID implies that R is Noetherian. Noetherian. So therefore, X is empty. X is empty means you can write every non-zero non-unit element as a product of irreducible elements, i.e. every non-zero non-unit element of R is a product of irreducible elements. Therefore, R is a UFT, unique factorization domain. Let's claim. So PIDs are UFT. Every PID is a UFT. Now, okay, let me finish here. Later, we will show that every non-zero non-unit element is a product of prime elements essentially in a unique way, just like as in integers. And let's finish this lecture here.